In this screencast, I will demonstrate how to version software projects using the Git distributed version control system. Let's start right away with creating a new Git repository. Let's create a new folder called example and create a Git repository in it using the git init command. Git init just created a new folder for the repository called .git. You already can see one of the advantages of distributed version control systems here. A repository can be a completely local undertaking requiring no central server. Your own files and folders are called working tree. Currently, the working tree is completely empty, so let's create a readme text file so we have something to commit to the new repository. Committing files to the repository is done through a staging area called index. The index essentially is a snapshot of the project files. For our new repository, it is currently empty. We can compare the index with our working tree files using Git Status. We can see here that we have a new file readme text in the working tree, which is not present in the index snapshot. The status can also be shown in a more dense format using the Git Status -s option. To add the readme text file to the index, we used the git add command. This is reflected immediately in the status. Please note that git add takes a full snapshot of the file. We can observe that when we change the file again. Git Status -s will show that the file is different in working tree and index. Let's add this change as well using git add. Now that we have our changes in the index, we can tell Git to create a commit from the contents of the index using the git commit command. Please note that committing is a completely local operation, not related to sending something to a remote server. It just takes the contents of the index and stores a snapshot of your project files as they were in the index. We can see the history of our project using git log. Here's the first commit we just created. Different from traditional version control systems, commits are not numbered. There is no such thing as revision number 1. Instead, a commit gets assigned a hash of the snapshot contents. This may look a bit awkward at first, but it brings a huge advantage with it. Every commit, which is a full snapshot of your project files, is identified by a tamper-proof signature of the contents. If somehow only one byte of the contents or the history of your files changes, you would end up with an entirely different hash. So Git guarantees that you get out what you put into it. Also, you don't need to write the full commit hash when you want to refer to some specific commit. You can always abbreviate them. The first 7 characters are usually enough to identify one commit uniquely. For example, you can show some specific commit using git show. We could specify a full commit hash here, but we can also abbreviate it and we will see the exact same output. To recap what we just have seen, the workflow for editing files in a Git repository consists of making the changes in the working tree, adding these to the staging index, and creating a commit from the contents of the index. You can also perform these steps using graphical tools. Git ships with Git GUI. Let's just change the file again. Now we just can fire up Git GUI. We will see the changes we just did over here. This shows the difference between the working tree and the stage. This list over here shows the changes between the working tree and the last commit. We can just stage and unstage files using Ctrl-T and Ctrl-U. We also see the actual changes we did over here and can create a new commit over here. As you do these steps again and again, you will create a new commit each time, pointing back to the previous commit. We can see that in the log, using the git log --pretty = raw option. We can see that the second commit we did points back to the first one. So the parent ID of the second one is the commit ID of the first one. This is how Git keeps track of the project history. It just stores snapshots of your project files as commits. These commits point back to the commits they were created from. Of course, all snapshots are saved in a very efficient manner, occupying only a fraction of disk space compared to a full copy of all your files. When looking at the history, you might want to use a format that is a bit more compact. like git log --pretty equals 1 line. I recommend to define an alias for an even more compact log format. You can get a snippet to paste from gist.github.com/515937. I keep some useful default settings over there, and if you get the config for alias.lg and paste it into your terminal, this will define a new command alias lg, which calls git log with some additional options. This shows you a very short colored log output using shortened hashes and relative dates. If you look at the full commit messages of the commits we just created, you will find information about the committer here. Git guesses these from your user and host name, so you should configure them globally using the git config command like this. This configures the username and the user email globally. If you omit the ---- global, the settings will be only for the current repository. I also recommend to activate colored console output using the color UI option. This activates colored output for commands like git log. You can read about all the other git config options in the man page. Just call git help config for this. Also, there is lots of information in all the git man pages, for example see git help log. Let's have a look at some more commands which are often necessary when working with repositories. You might want to undo changes. How to do this depends on where the changes are which you want to undo. Let's say you have just changed some file in the working tree. We can undo this change using Git Checkout. Git Checkout restores the file from the index, so we will have a clean working tree afterwards. You can also do this using Git GUI by reverting the changes. What if you've already added the changes to the index? You can undo this using the git reset command, but that's a bit tricky. I recommend to do this operation using Git GUI as well, where you can just unstage the file and revert the change, and you will have a clean index and a clean working tree again. What if you have already committed your changes? Let's say we find a problem in the last commit we did and we want to revert this commit. We can do so using git revert. Git revert creates another commit which reverts the change we just did. You can also revert older commits using this command, but this can cause a conflict if the commits in the meantime changed the same contents. I will show you how to resolve such conflicts later on. Sometimes you might want to see the difference between commits. So far we've only used git show, which compares a commit to its parent. If you want to compare two specific commits, you can use git diff with two commit IDs. If you want to see the diffs for the complete history, use git log -p, which shows the log including all the patches. We have seen so far how to refer to specific commits using their hash value. Sometimes it's useful to put a label on some specific commit, so it is easier to refer to that commit later on. For example, you might want to label release commits with their version number. You can do that using the git tag command. For example, let's tag the current commit with 1.0 and the first one with 0.9. This created two tags, which we can see in the commit log now. Tags can be used everywhere where you can use a commit ID, for example for git diff. So far we have seen how you can create commits and work with them. Up until this point, all the history of our repository has been linear. Let's say we want to develop a new feature for our project. This is something very large and we want to keep those changes separate from other changes. We can do that using branches. All the time we were already working in a branch called master. You can see this by calling git branch. This shows that there is one branch called master and that it is active. A branch can be compared to some extent with a tag. At all times a branch points to some commit. You can see that using git branch -v. The branch master currently points to the latest commit. To fork a separate branch, we can use the git branch command again. This created a new branch called new feature, pointing to the same commit. You can also see here that master is still the active branch. To switch between branches, use the Git Checkout command. By the way, there is another useful snippet on the Git page for working with branches. If you add this to your bash or C file, you will see the current branch in your command line prompt. Let's start working in the new feature branch. Let's do a commit over here. Now, what happened to the branches? The master branch is still where it was, while the new feature branch points to the new commit now. So a branch is only a pointer to some commit. Whenever you commit something, this pointer of the active branch is moved forward to the new commit. This is everything it takes to track branches in Git. Let's say we are finished with working on our new feature for the moment and want to continue working on the master branch. We just switch back to the master branch using Git Checkout. This will set the active branch back to master and reset the index and the working tree. So we see the exact state we had before forking off new feature. Now, what happens if we add some changes here and commit these as well? A new commit was created based on the latest commit in master, and master will be pointing to that commit now. Let's say we have completed the new feature already and want to get it back into the master branch. This can be achieved using Git Merge while we are in the master branch. If all goes well, there will be no conflicts and Git will just create a new commit containing the changes which have been made in both branches. In our case, we changed the same lines in the same file, so we will have to fix the conflict first. In the file, we will see the lines as they were in master and as they were in new feature. So let's fix this conflict, remove the markers and add the change. We can then commit the merge. Git created a new merge commit now. If you have a look at the raw history, you will see that this new commit points back to the two commits it originated from. This gets a bit clearer when you have a look at the history using the graphical log viewer Git K. A new merge commit was created, merging the two separate branches new feature and master together. Another helpful capability of Git branches is that you can merge them repeatedly. When I switch back to the new feature branch and do another change over here, I can then merge new feature into master again. This merge happened automatically, because Git knew that some commits have been merged already. Also, the changes didn't cause any conflict because in new feature a line was added and in master no change happened at all. So far we have only worked locally with the repository. What I want to do now is to share the example repository. For this I will use GitHub. GitHub is a hosting service for Git repositories, which makes it very easy to create and manage repositories. So I create a new repository over here. After the repository was created, I can use this repository URL to push and pull contents from my repository. Pushing and pulling contents between Git repositories is done through remotes. A remote is a connection from one Git repository to another one. So what I do now is I add this repository on GitHub as a remote named origin to my local repository. This is only configuration. I have now a connection to the repository on GitHub and I can pull and push commits from over there. This allows me to push my master branch over to GitHub. All the history of my local branch was just pushed to this remote repository and a new branch was created on GitHub. You can also see this on the GitHub site. The full history of the master branch was replicated on GitHub by pushing. All the commits we did locally are present over here now. So whenever you push or pull between Git repositories, you are replicating the commits and their contents. Now, what happens when more than one person works with a Git repository? Let's say we have another person who also wants to work with this project. He would create a local copy of this repository to work with the project. This is done using the Git Clone command. I just clone the repository at the repository URL. Now I got another local replica of the repository on GitHub containing all the commits. And I can just start working in my local master branch. Let's commit a change over here. Now I need to push the new commit over to GitHub. You can see that this has not happened yet in the log. Master points to the new commit, but my copy of the master branch on GitHub, called origin master, still points to the previous commit. Now I push the commits I did on my local master branch to the master branch on GitHub. This also updates my origin master branch, so after pushing, both branches point to the latest commit. Also, the GitHub page shows that everything worked okay. So what if different people work in their local repository and want to push these changes? So I go back to my other clone of the example project and commit a change over here as well. Now, when I try to push this change as well, this is rejected because the tip of the master branch on GitHub is not in the history of my local branch. I have to merge this first. Merging happens automatically when pulling changes. Here I did a change to the same contents, so I need to fix the merge conflict first. Now, the tip of the removed branch I want to push is contained in the history because of the merge commit, so I'm allowed to push this. Thanks for watching the screencast and have fun versioning your projects using Git.